Today we're going to be studying simple harmonic motion, and what's more harmonious than Jack? Nothing. 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 Let's first get some definitions out of the way. Oscillations are motions that repeat themselves. Everything else after that is an oscillation, but repeating themselves is the start. They ought to not just be oscillations, they have to be periodic, which means that they repeat themselves at regular intervals. That's the second condition. And then the third condition, the biggest condition for a simple harmonic oscillator, is a motion that's force is proportional to the displacement. So it's only oscillations and periodic motions that have a force that gets bigger as it gets farther from its equilibrium point. So with a spring, you have a mass and a spring. As you pull it, you get more and more and more force. Same going this way, force up, and so we know that has to be simple harmonic motion. This is what we start with. So, when we start with this, we know that force is proportional to displacement. And since force equals ma, and m is a constant, we can take m inside of our constant. It doesn't say what the constant is yet, so we can say that acceleration's constant is a constant times x. Since acceleration is the double derivative of displacement, we get our very first differential equation. Differential equations is the class that comes after multivariate calculus, but we can handle it because it turns out that differential equations, you have to first just make a guess as to what you think it's going to be and then work out the consequences and see if your guess was correct. So we want to make a guess as to motion that starts here, gets faster, 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 slower, 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 faster, 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 slower, 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 faster, faster, faster. Looks like that. And it turns out that we have a function that looks just like that. Take a couple seconds and look at it and tell me that you think this looks like a cosine function. So we're going to guess cosine, work out the consequences, and do our very first differential equations. Thus, continuing the magic. So I don't want to just do any old cosine. I want to do every cosine. So I have to include some constants in my cosine functions. I want to include any height amplitude. So amplitude is how big I make my function. So this is amplitude. If I make a nice big function over here, this is amplitude. So A just says how much up and down it goes. My next constant, omega, tells me how fast I'm moving back and forth. Because if I go and put this constant equals omega, 2 pi over omega in, I have cosine of 2 pi t times time. So that means that every time my time equals a multiple of the period, I get 2 pi. So that means every time I get through one thing, which is 2 pi, is when my omega is 2 pi over my time gets to that period. And omega tells me how fast it goes. So if omega gets bigger, it's going back and forth faster, faster, faster. But it's related by my period there, and that's going to become important later. And my last one, which is phi is just a phase constant. So if I had something that was going like this, and I move the whole thing over, so it started here instead, and I'd have to dot something over. This is the phase, how much I move it over. So I could use phase to make my cosine into a sine if I started it in the middle. Essentially, phase is just where in the process I am. And this is position as a function of time. I'm going to use all these equations to sort of analyze it. And don't forget that frequency is also 1 over the period.
All right, it's getting a little sweaty in there, so I'm coming out of the mask, as they say. Once we set up our equation with our variables in there, then we can look at what happens when we take the derivative of it. If we take the derivative of the sine, we get the negative cosine, but we also have to use the chain rule to get the omega on the outside. So my velocity function as a function of time is minus omega a sine omega t plus phi. And then I do that again when I go from sine to cosine. I don't get a negative, but I do have to, again, take the derivative of that, which gives me omega squared on the outside a times the cosine. But notice that my x is cosine and my a is cosine, and so I get a function where a equals minus omega squared times my x, and I know that I guessed correctly because I get a equals constant times x, and my constant in this case is minus omega squared, and that's important when I'm trying to figure out period in a couple seconds. But this is differential equations at its heart. I'm guessing that it's a cosine, and I work out the consequences, and if it gives me what I want, I know that I guessed correctly. And it did give me what I want, so I did guess correctly. This is the first one. It's really easy. Later on, things get a little more difficult. That's in your future, if you keep up with math. A little more details on each of these. So if we go to velocity, where we take the derivative of x with respect to time, this is what I'm taking the derivative of. I get this nice, easy equation. Notice that my amplitude of the velocity is omega times the amplitude of my displacement. And so that tells me that the maximums of my velocity and the minimums of my velocity are plus or minus omega a. And it means that when x is maximum, my velocity is minimum because I go from sine to cosine. And I knew that from my simple harmonic motion, but this is just proving that it is the case. And when x is 0, Vt is at its max. Same details with the acceleration. So when I do acceleration, I take the derivative of that velocity equation that I just got. And notice that that means my maximum acceleration is when omega squared a is my number. And so if I know what my omega is, which I will in the future, I'll be able to find out what my maximum acceleration would be pretty quickly. And notice that it's minus. So that means that whenever acceleration is at its maximum, the displacement would be at its minimum. So it's going in the opposite direction. Now we knew that from a spring, right? We knew that when my displacement is a maximum out here, my displacement is positive, but my acceleration is negative. But this is sort of, going through these equations and making sure they match up with our expectations for what simple harmonic motion should do. Just a quick graph of each of them with respect to time. Notice that x starts at its maximum amplitude. V starts at 0 because you're letting it go when you've pulled it out the most, for example in the spring. My acceleration would be negative, and as time goes on, I get to a point right here where my velocity is the fastest, no acceleration, no displacement, that's in the center, and it keeps going, and you can follow through all the things, but notice that they have the same period, all of them have the same omega in them, in their equations. They just are off a little bit. This one, sine to cosine, 180, right? No, 90 off. And then the acceleration is the same, just flipped over on the other side. Different amplitudes, though. So I'm going to keep going in our kind of overview of the simple harmonic motion thing by looking at the total energy. We know that E total has to equal the potential plus the kinetic. For a nice spring, a Hookean spring, we have this as our potential, and this as our kinetic energy. And we can put that in terms of our cosine and sine functions. And so we get that and that. Notice my velocity has the negative omega a there. We plug them into our two equations. So you go 1/2 k x squared plus 1/2 mv squared. And then when we do this v, we get m omega squared here. And m omega squared is the same thing as k. And so then we get 1/2 ka in both these two functions. We separate that out. When we do that, we have cosine squared plus sine squared, which we know is 1. So this proves the fact last year that I told you that the total energy stays the same. I didn't say how you know that. You just had to sort of believe me. But this is proving that it's true. But proving conservation of energy true, that's always fun. But I like it when we get nice things like sine squared plus cosine, and everything works out nicely. Math magic. Boop. That leads us to this graph that we had last year, but now we've proven this dotted green line up at the top. And the other two we already knew. The red one is kinetic energy, the blue one is potential energy. This is a position versus energy graph. So we know the maximum displacement's out here, the maximum acceleration's out here, that's on both sides, and the maximum velocity is in the middle. Maximum x means maximum acceleration, maximum kinetic energy means maximum speed. And just going back over that graph again, we definitely use that a lot this year. Here's another little quick graph. This one is energy versus time. Sorry, time's on there, And notice we got our maximum potential. It goes on to minimum potential, maximum, minimum, maximum, and that's 1 period. Yeah, and this is the potential. The kinetic starts at 0, goes up to its maximum, down to its minimum, maximum, 0 period. And we can draw this too, and remember this right in the middle is when we have half our energy in each, and then across on there. That's at a different point on our graph, you know, this one where it's going like this. It's those points right there. Extreme snack time. I'm kind of reeling from Halloween and eating so much chocolate, and so today's extreme snack is vegetables. See all the lovely vegetables all around it, but this is vegetables touched by Jack. And so everything turns Halloweeny when Jack touches it. So we're having vegetables, but we're having vegetables turned into sweetness. I actually have 2 snacks for you this time. This right here is a green pea lentil snap. Very vegetable-y, right? Right? Except that it is salted caramel flavored pea snack. We'll see how that goes in a second. The other thing, and this is a new one that this just came out this year. I've been looking for these and haven't found them before, and this year I found them. The other snack we have is a soda, but this soda is celery soda. It's celery flavored soda. I don't know how this is going to go. I don't like celery by itself, let alone as a soda. This one is not new. This kind of celery has been bottled since 1868. It has been in New York delicatessens. Apparently it goes good with pastrami. I don't know, but it's an internet phase sensation right now, and we're going to give it a try. These you can get at Randall's. Celery you have to get online. It took me a long time, and I had to buy like 20,000 of them. You couldn't buy like one. All right, this is what the pea thing looks like, and here goes the salted caramel part. Holy cow, that one's good. Pea goes well with caramel. All right, hope for the best on my celery soda. You're gonna try this one too. Celery, I don't like it. Ugh. Okay, it started weird. Okay, I'm not liking that as much as the peas. I'm gonna have more peas. I have let my son have the celery soda. He's addicted to this. He hasn't tried this one yet. Oh man. Yeah, this is the winner. Salted caramel, pea snack, definitely. Celery soda. Maybe I need some pastrami for this one. I don't know. Hey, there's 2 types of this. Look, there's a green one and an orange one with more caramel in it. It's like a little caramel or a lot of caramel. I'm not sure there's going to be left for you of that. That's pretty good. Okay, let's talk about Hooksaw Spring. We know the force for Hooksaw Spring is negative kx, but since F also equals ma, we know the A for our any oscillator is omega squared x, we can plug these two equal to each other. Negative kx equals negative m omega squared x. Notice that means that the k, that constant, you know, we're talking about, is omega squared because omega, m omega squared, because that's where k, and since they're both equal to x right there. So as we cancel out our x's, we get that. And solving for omega, we get omega equals the square root of k over m. Nice. Now we have an equation that says omega equals 2 pi over period. So I plug in k over m there, and we can solve for t. T equals 2 pi over the square root of k over m. So you flip m over k, and we end up with that equation we had last year that there was no explanation for last time. Now we know enough to explain it. I love Physics C. It explains everything. At least the important things. I'm gonna have a pee. You look at this. Make sure you get it. I love it. It's wonderful. Quick example problem. What we might see on a pretty easy C question. They give us a spring with a mass of 0.68 kilograms, K of 65, maximum compression or stretch of 11 centimeters, change it to meters. That's our A. That's what our force is. We know our force is negative kx, so we just throw in our k and our x. We get our answer for force. They might ask us what's the block's angular frequency. Angular frequency is omega, so we just use that equation we just solved for. Square root of k over m, we get this. If they ask us for the frequency, we can take 1 over that omega. If they ask us for the period, we can throw it into our 2 pi square root of m over k business and have our answer for period. So they asked for this one this time, but they could ask for either of these other two. Our maximum displacement is nice and easy because they gave us what it was up here. We just have to remember what to use. And then when they ask for the maximum acceleration, we just do F equals ma. For the F we already solved for, we know the m, so we can find a. Pretty easy, kind of, at least the mass spring ones. Moving on to our period of a pendulum, right? Okay, so when we have a pendulum, it's moving up there, and it's going to move back down there. My restoring force in a pendulum is going to be mg sine theta, this part of mg. So my force is mg sine theta, right? And I told you last year that the pendulum only works for small angles, right? And it's when sine of theta is about equal to theta. So what we do in this is we take away sine theta and we put theta there instead. Now, we don't leave theta because we want to put it in terms we know, but since the angle is always equal to the arc length over the radius, in this case that's x, the whole distance that I've moved, over L, which is the length of my spring, I can plug x over L in. When I do that, I get this equation here, which looks very familiar because it's some constant, m doesn't change, g doesn't change, L doesn't change, times x, with a negative in front of it. That's very similar to my spring one, which is negative kx. I just have a different k. My k is now mg over L. So then I can take my period equation that I've already got and plug this in for k and simplify, and I get exactly the period equation from last year. You can prove anything. Don't let anybody tell you any different. A couple more quick ones. It turns out that we can do a pendulum in a car accelerating forward. If a car is accelerating forward, we don't just have gravity going down, we also have acceleration going backwards. Because the tension's going that way, we know that we have two different forces that give us basically an overall acceleration of this object, and we call that acceleration g prime. To get g prime, we do a squared plus b squared equals c squared. And once we know that g prime, that's what my pendulum is going to rotate around. And that changes the g, essentially, in my equation. So my equation for an accelerated motion is just 2 pi L over g prime. Remember, a squared plus b squared equals c squared, with gravity there, the acceleration that going forward there, and g prime there. And you can figure out the period of a pendulum, car accelerating forward. Nice. Don't forget that we take our mass spring, we put them up and down instead of right and left. That doesn't really change any of our equations. It turns out that gravity cancels out in our energy equations. If you're interested in that, tell me in class, and I'll see if I can work through it on a review day. It takes a little bit of time to get through, but it's interesting, so maybe you should say yes to that. It's up to you. But essentially, when you're going up and down here, all you have to consider about is mv squared and 1/2 kx squared at the top. Same as if it was sideways, which is nice, makes life easier. So we do have to do things a little different when we get to C. It turns out that when we say that the energy total is negative Ka squared, it's really only negative Ka squared at the beginning. We know when we take a spring and we let it go, the amplitude gets smaller and smaller and smaller and smaller and smaller. And that's what we have to deal with now. We have damped oscillation, oscillation that gets smaller. And damping is always an exponential decay, and so we get e to the something. E is sort of a made-up number. You've probably talked about it in math, and whenever you have a decay, you have a negative up there for your E, and so your graph looks sort of like you start at this value and it goes down, getting closer and closer and closer to 0. So we have a time up in our equation. We also have a constant b. That has to do with the spring and all the different variables in there. We'll talk a little bit about that, maybe. But since we do a lot of different exponential k's in the future, we also talk about what's called the time constant. Tau is the time constant. It's what we multiply, we divide time by. And when we get to the time constant, we know that we have e to the negative 1. times our original value. And that part, e to the negative 1, is about 0.63 of my original maximum. And we don't really need to know that quite yet. All we really need to know right now is that to get to the reality of what happens with springs, we have to throw a little e in front of that to get it dampened. So I got another thing we got to deal with. It turns out that when we found the omega earlier, we're finding the natural omega. So if we pull it down and let it go, there's a frequency that it's going up. But we can also take a force and apply it at some other omega, and it creates some kind of motion. And it turns out that if it's not close to the original omega, we just have to atom principle of superposition with my two graphs, and you can do another one that's going like that, whatever. Find all the different amplitudes at the time. It's only when that force frequency gets close to omega aught that we get some interesting things happening. When we get our omega getting close to omega sub 0, that's when we get what's called resonance. When we get our omega close to the natural frequency of whatever it is we're talking about, the amplitude gets bigger and bigger and bigger and bigger and bigger. And we get any kind of sound that we ever hear. Some examples of that are when you pump on a swing. If you push your feet at the same as the natural frequency of the pendulum of the swing, you get faster and faster, higher and higher and higher, and that's great. Earthquakes have a lot of resonance in them. Musical instruments, every note that you ever hear, the amplitude would not be big enough unless it had a resonance in it. Yeah. So it turns out that even with the same frequency as the resonant frequency, there's different types of resonances we get depending on how much damping we have. You know, we talked about that damping. If we have a small amount of damping, we get a huge spike there in our omegas, in the amplitudes, based on how close we get to omega aught. We call that a big Q. The Q factor is how pointy this little graph is. If we get a lot of damping, we get a small amplitude maximum. That's what we want, like in an earthquake, for instance, in buildings. We want our Q to be small so we don't get much amplitude, even at our resonant frequency. If we had no damping, we'd get infinite there, and that'd be awful. So we want at least some dampening so we get it. But the higher the amplitude, the more damage happens, like in earthquakes or in that example with the bridge where the soldiers are marching in step and the bridge got slower. So yeah, you get the idea. We'll watch a video on this. You're going to like it. I like it. Because we're dealing with exponentials, we have to remember that the derivative of an exponential just gives us that same exponential. That's a nice derivative, which means that the integral of an exponential just gives us the exponential. And while we're talking about that, we need to talk about the one other power function. When we have the integral of x to the negative 1, we can't just take that up 1 because it wouldn't give us a value. And so it turns out that gives us the natural log of x. And that means that the opposite of that is up here. When I take the derivative of the natural log of x, we get 1 over x. I'm hoping all of you have at least done this part of that in class. I know that the BC people have, and you've probably even done this side. And we'll talk about it in class because I'm not sure the AP people have quite yet. We may have a little math to catch up. Okay, off to physics, off to veggie, especially if your veggies are covered with salted caramel. Oh, there's problems. There's problems with this math. All right, off you go.